speaker is Takahiro Morishita, who is a postdoc at the Space Telescope Science Institute. And he will be telling us about SuperBoRG and what it can do for research for quasars.
Thanks, Sarah, for the introduction, and also to the organizers for this wonderful conference. I also thank to everybody for tuning in this talk. My name is Takahiro Morishita from STSCI, and today I'm going to talk about SuperBoRG, which is our latest program of HST, collecting a bunch of images. And primary focus is on the exploration of luminous galaxies and quasars at this high redshift. Collaborators are listed here, and these are mostly from previous BoRG collaboration. So I am going to introduce this project as well. So, all right. So let's start with a big picture. So here I'm showing a beautiful image of the universe with some of high redshift quasars known today too, and asking myself, why is high redshift so important? Why do you want to find quasars in this redshift? Well, I don't think I need to repeat this, as we just saw a nice review in the previous talk, but just briefly, this epoch, known as the epoch of reionization, is the critical time that the universe transitioned from completely neutral to almost ionized. And we want to know the source that ionized the universe and when and how they did it. So it is important to see and study the source of light from that epoch. In fact, we start seeing some light from this epoch with water field imaging data, for example. In fact, all the quasars here are from ground-based observatories. And then asking ourselves again, why is luminous source so important? Specifically, why do we want to find new high redshift quasars? I think there are two important things that I can say here. The first is, as you see in the left, we can measure neutral fraction of the universe from individual sources by carefully looking at the spectral shape or damping wings. So finding new quasars at this redshift means that we increase the data point, as we see here. At the same time, because these are from individual measurement, and these are independent from the statistical measurement from galaxies, for example, and these are complementary. Another point is, of course, evolution of supermassive black hole. The discovery of extremely luminous quasars at this high redshift imply that rapid growth and possibly very heavy seed mass in the first place too. These findings have actually challenged and also advanced our theoretical understanding too. So to better understand the evolutionary picture and also the transition of the universe, we need more data points at higher redshift, and in particular of more ubiquitous, less luminous population as well. So we are now trying to go beyond the limit, but can we go that easily? So, but it's challenging, as we just saw. This is because beyond the current limit, the Lyman break go into the near-infrared wavelength range, as I'm showing here. And at that wavelength, we start suffering from the significant background sky level, and also the source itself, the brightness becomes fainter as we go higher redshift. So near-infrared filters are available, of course, from the ground, but we may only be seeing the luminous end of this population. And these sources, of course, become even rarer at higher redshift. So we now may need to switch, or at least consider to switch to space-based at some point. Currently, the Hubble is the only facility that can detect such faint light with the wavelength coverage up to 1.7 micron. but its field view is so limited and tiny, as I'm showing here on the right side. This is a picture of cosmic structure at redshift 7, taken from simulation. And even with the size of candles, like here or here, the pointing could fall into the void region, and we may find nothing from HST that's possible. So as a summary, to go beyond the current limit, we need exquisite near-infrared sensitivity and also wide field survey, ideally from many random pointings, wide field pointings, so that we can minimize cosmic variance and also sample the universe unbiasedly. And that's why we started this SuperBoRG project. As I mentioned at the beginning, we have had actually the Borg collaboration almost 10 years, but that was originally aimed for luminous galaxies, not for quasars, through the pure parallel HST mode. So we have many random pointings all over the sky. And now, after 10 years since we started, we have collected a huge data set, as I'm showing here. And that means that the data set allows us to explore even rarer populations, which is quasars at this redshift. The data set is now in preparation for public release through MAST. So catalogs and images will be published. And of course, these are from HST and data HST quality. So these are also good for low-Z science and intermediate redshift science as well. And I'd be happy to collaborate or just provide this data if any of you are interested in using them. So now let's go back to the quasar search. Did we find a new quasar? Well, the answer is still pending, but we actually found something interesting from this SuperBoRG collaboration. First of all, to search or to select quasar candidates, we apply color cut on the left here, and also morphological selection by looking at the source morphology. The color cut is actually designed to pick significant Lyman break galaxies and also blue UV slope. So the selection window is shown here. One good thing that I like to mention here is that as we go higher redshift, then the contamination becomes less. So here, I'm also showing the brown dwarf populations, which we think as a low-Z interlopers. As you see here, if we go higher redshift, then color becomes redder, and then it's become more distinguishable, which means that we have cleaner sample. And the same is shown here on the right panel. I'm showing 2 SEDs of brown dwarf and also redshift 8 SED. As we go higher redshift, then Lyman break shift to longer wavelengths. So that will be easier to separate these populations. So from these selections, we found actually 3 point source candidates. We are confident with the number because we also found about 100 galaxy candidates from the selection with extended morphology. So this number is consistent with luminosity function at this redshift. So the number is pretty robust, I believe. And to make sure that these 3 point sources are not low-Z interlopers, we also did SED fitting analysis and also astrometry for one of them, because that one of the object has 2 epoch imaging data, so we can just see the difference in the position of the source to measure astrometry. Among 3 candidates, one of the middle one, this one, is particularly interesting because you can see IRAC channel 2 excess here. The flux excess is significant in channel 2, So let's take a deeper look at this object. So here I'm showing the SCD fitting result. And at this best fit redshift, that excess can be attributed to the H beta and also oxygen 3 lines. So that is telling us this is extreme object. By taking the residual of the SCD versus flux excess, we measure that equivalent width is around 3000. And that is one of the most extreme object at this redshift, shown in the left bottom. And given the maximum contribution from H beta is not high, it's around 1500 angstrom. So it's fair to think that the ISM of this object has some contribution from metal and also very high temperature. Another exciting part is that there is a good correlation between flux excess in channel 2 or channel 1 of high-redshift object between this and Lyman-alpha flux excess. So we are very excited to see the spectrum of this object. But actually, life is not so easy, and we did not see any significant emission from the spectrum taken at Keck. We spent a couple nights and also got archival data from the past years. And now we have in total almost 10 hours exposure of Keck MOSFIRE, but still no emission lines. So this may imply one of the following. Maybe this object is located in significantly neutral region, or the line is actually there, but since it's very broad, we could not detect. But still, we can get some numbers out of this deep spectra and non-detection with simple assumptions such as case B or dust attenuation from SCD fitting and oxygen 3 H beta ratio. We can get the upper limit for Lyman escape fraction with this simple formula. But again, this is for unresolved line, and the case would be different if there's broad line. So this is going to be my last slide, but before I end my talk, I like to mention possible nature of these point sources from their number densities. From number densities, we can tell that the population is not likely typical quasars. This is because the number density of lossy quasars. So I'm showing here quasar luminosity function at redshift 6, not 8, but they are much lower than what we found here. The magnitude range is actually slightly fainter for our case. So maybe there is a chance that the slope is much steeper at this faint end. But with current dataset, it's hard to conclude anything. Of course, with Raman Space Telescope, we can do much better. With its almost 100 times larger field of view, I'm showing the field of view of Raman as well as the total area of SuperBoRG. We spent with HST almost 10 years to collect this area, but with Raman, we can do this with one single shot, which is amazing, and I'm pretty jealous about it. So as a conclusion, while we don't fully understand this new population at this point, and we definitely need follow-up observations, I believe our work initiated a new interesting field, especially for magnitude range, where luminous galaxies and low luminosity quasars co-locate. And hopefully follow-up observation will reveal more details about this population and advance our understanding of early source of the light and the universe itself. So I'll leave you with the summary slide, and I'm happy to take questions. Thank you.
Thank you, Takahiro. If everyone can give you a round of applause. I'll start with a question. So what fraction of galaxies and these redshifts which show an IRAC excess don't have Lyman-alpha?
Sorry, now can you hear me?
Yeah, now we can hear you.
All right, perfect. So I repeat myself. So I don't know exact number for that, but it's definitely interesting to take a look. And my impression, although, is that excess means that Lyman-alpha presence. So it's pretty likely, and that's why we were so excited to see Lyman-alpha.
And another question. Could these be compact galaxies at redshift 8 rather than quasars? How confident is the point source classification in BORG, where the data is typically not dithered since it's pure parallel?
Yeah, that's excellent point. Like you say, the BORG is not dithered in image, but we are confident with the image quality with some previous tests, and they actually, the point source are clearly selected out of extended sources. But back to your point that how we separate super compact galaxies and quasars, it's difficult and it's challenging with HST by itself. So to do that, we definitely need a spectroscopic follow-up for to be sure that what we are looking at is quasars.
Thank you again, Takahiro. Very exciting results.
Thank you very much.